Hi. Before I begin, I'd like to acknowledge and thank my co-authors, Neve, Omer, and George at Brown. Our paper is on learning Markov state abstractions for deep reinforcement learning. Okay, let's jump in. Our big picture goal is to enable decision-making with rich observations. This is a very important problem on the path to general purpose artificial intelligence. Suppose we have an agent with some sensors. Those sensors provide the agent with rich observations about the world. For example, maybe the rich observation is an image of a chessboard. The important thing to realize is that in general, the agent doesn't get to choose its sensors. The sensors are fixed, regardless of whether those observations are in a good format for decision making. Luckily, the agent doesn't need to base its decision making on those rich observations. It can use an abstract representation instead. For example, it might recognize the different piece types and encode their locations in this chess game as discrete positions. Frequently, these abstract representations are learned implicitly as a byproduct of doing deep reinforcement learning. So maybe we should ask up front, can we just use deep reinforcement learning here? And the answer is yes, but with some caveats. Generally, deep RL works better when we have an abstract representation as input. And then we frequently learn an even more abstract representation internally. The problem is, the agent doesn't get to change its sensors. So unless we want some system designer to specify in advance the abstract representation that should be used for each potential future problem, we need our agents to learn these abstract representations themselves automatically. And currently, deep reinforcement learning isn't enough because of a problem that I like to call the representation gap. When we train deep RL agents, even on a very simple problem like grid world navigation, it makes a huge difference what feature representation they're using. Imagine for the visual features, we have a noisy camera looking down on the grid world from above, and for the expert features, we know our precise ground truth XY position. If we train a DQN to reach the goal using these features, we find that it learns much faster with the expert features than the visual ones. This difference in learning performance is what I'm calling the representation gap. We see this phenomenon for lots of different problems. Not just grid world navigation, but also games and continuous control. Across the board, performance with expert abstract representations tends to beat that of visual features. Going from the rich observations on the left to something more like the expert ones on the right is the goal of state abstraction and representation learning. If we want to learn good abstract representations, we ought to look at the ones on the right and see what properties they have. One of the most important things to notice about these expert representations is that they are both concise and Markov. Why do we care about having Markov abstract states? Because we want to do decision making in the abstract state space, where our goal is generally to find an optimal Markov policy. That means that the agent's behavior only depends on the current abstract state. But these abstract representations may not be Markov, even if the observations are Markov. The reason is that the abstraction necessarily throws away information. Discard too much information and the representation cannot accurately characterize the environment. Discard too little, and agents will fail to close this representation gap. So abstractions must balance between ignoring irrelevant information and preserving what's important for decision making. To visualize what it means for an abstraction to be Markov, let's go back to the grid world example. The MDP is defined in terms of some hidden state information. We're calling that S here. And then to model the rich observations, we assume that there is some sensor producing our observed states. We don't get to see the hidden states, and we don't know how the sensor works. But we just assume that these observed states are also Markov. So essentially, we're in a block MDP. And that means that if we're given a state X and an action A, we have everything we need to predict the next state X prime and the reward R. We assume that we can do this, so the observed state is Markov. But these rich observations might not be ideal for learning. So we encode the observed states using an abstraction function, phi, and get an abstract representation z. Here the orange circles show the encoded states. For an abstraction to be Markov, we need the abstract state z and action A to be sufficient for predicting the next abstract state z prime and the expected reward. There are a variety of representation learning methods for incentivizing Markov abstractions, including pixel prediction, autoencoding, biosimulation metrics, and others. But these generally tend to require either restrictive modeling assumptions or involve estimating probabilities over the rich observations, which is challenging, or they need dense reward feedback, so they're impractical when rewards are sparse or when representations need to be learned prior to receiving rewards. Our main results are threefold. First, we introduce sufficient conditions involving inverse models and density ratios for a state abstraction to be Markov. Then we present our model and show that simultaneously explaining why and determining whether state transitions occurred encodes the theoretical conditions that we need and thereby encourages Markov abstract states while avoiding many of the drawbacks of existing methods. Finally, we show experimental results where our objective leads to state-of-the-art learning performance. Our main theorem says that given an MDP and an abstraction phi, if the following two conditions hold for any abstract policy, one, that the inverse model probabilities are equal for both abstract and ground state transitions, which says that the distribution over actions for a given state transition is the same whether it was an abstract transition or a ground transition. And two, the next state density ratios are also equal, which says that we know how much more likely next states are, both abstract and ground, when we condition on a particular abstract state. If both of those conditions hold for any abstract policy, then phi is a Markov abstraction. To give you a sketch of the proof, we'll need to put three things into our toolbox. Two are the conditions that I just mentioned, and one is this bit about having an abstract policy. Let's rewrite the abstract policy so that everything is in terms of probabilities. Okay, now I'll move these tools over to the left so that we have some room. If we look at the first equation, which comes from the inverse model condition, we see that the left side is conditioned on z, but the right side is conditioned on x. We can take the expectation of both sides with respect to x being drawn from abstract state z to condition both on z. Once we do that, there are three terms that we can transform with Bayes' theorem. These three give us back the abstract transition model, and we can do the same thing with these three. And we get a sort of hybrid transition model over ground states conditioned on an abstract state. Now we can combine terms and simplify. The terms on the left give us this density ratio, and the terms on the right give us another density ratio. The numerators are two different transition probabilities. And normally we wouldn't be able to compare them because they have different support. But since they're in these density ratios, we're okay. The way to interpret this equation is that it's saying each abstract state z is equally informative about future abstract and ground states. Hopefully this gives you some intuition for why we can expect these conditions to produce a Markov abstraction. The full proof relies on defining belief distributions over ground states, which I've hidden inside the expectation at the top, and showing that under the two conditions, those belief distributions are themselves Markov. If you're interested to see how we do that, check out the paper. Now let's talk about how we implement this. The first condition is about inverse models, and it essentially says that we need to be able to explain why each state transition occurred, and moreover, that our explanation shouldn't change based on whether it was an abstract state transition or a ground state transition. The implementation will take as input two consecutive observed states, and it will map those through the abstraction to produce two abstract states. And then the inverse model, I phi, will predict a distribution over actions that explain that state transition. The target is the actual action that caused the observed state transition, which is what drives the abstract and the ground state inverse models to be equal. Note that this objective doesn't require pixel reconstruction, it doesn't require learning a transition model, and it doesn't need reward information. Now for the second condition about density ratios. This one says that we can determine whether the state transition occurred. The implementation again looks at pairs of observed states, but now we'll swap out some of the x prime samples and replace them with fake samples, x tilde prime. The target label will be whether we have a real transition or a fake one. We encode the states again and feed the abstract states to a discriminator d phi, which tells us whether it's more likely that they were sequential states or non-sequential states. The ratio between these outcomes is exactly the density ratio we care about. And again, because the labels come from the observed states, we drive both ratios to be equal. The same benefits apply as before. We don't need pixel reconstruction or transition modeling or reward information. Now we're ready to define the model architecture. We start by encoding pairs of states using the abstraction. Then we send the abstract states into an inverse model, I-phi. This encodes condition 1. We simultaneously send them into a discriminator, d-phi, which encodes condition 2. And finally, since the whole point of all this was to do abstract decision-making, we make sure that the policy is defined in terms of only the abstract state. If you like, you can call this condition 0. We use this architecture to encode visual features from the grid world domain without any reward information into Markov abstract states. The representation that we learn is remarkably close to the ground truth hidden state information. You can clearly see the 6x6 grid structure in our abstract state space. Now remember that previously our learning curves had a significant representation gap between visual features and expert features. Now if we learn a Markov abstraction in advance, then freeze it, and train with the resulting representation, we're able to fully close this representation gap and recover the performance of the expert features. We also evaluate on a set of continuous control benchmarks from the DeepMind control suite. This time we incorporate our abstraction objective online alongside a reinforcement learning objective. And we find that Markov state abstractions achieve state-of-the-art reinforcement learning performance, beating every baseline in a head-to-head comparison on the majority of domains. So to summarize, we introduced sufficient theoretical conditions involving inverse models and density ratios for a state abstraction to be Markov. We showed how to implement those conditions as a practical training objective without requiring pixel reconstruction, transition modeling, or reward information. And finally, we showed that our training objective fully closes the representation gap without any reward information on a visual grid world domain, and additionally leads to state-of-the-art performance on the continuous control benchmarks. Check out the full paper to learn more, and thank you for listening.